In the previous episode, we've been busy building up this register file here. It has two registers, R0 and R1, two read data ports, which allows us to read two registers at the same time, and a write data port, which allows us to apply a value and then pick a register into which we want to store that value. And prior to that, we've been busy building up this program counter here and this program memory, which actually produces the instruction bits that we want to execute. And now since this register file is more or less done, the next step would be to combine the two and have a few instructions that can access the register file and interact with it. The simplest instructions that come to my mind here are an instruction to load a constant value into one of the registers and an instruction to copy a value from one register into another. These instructions are actually pretty common in processors. They're generally called load immediate, where the instruction actually contains in some of its bits the immediate value that we want to store in the register, and move, which is kind of a misnomer because we're not actually moving a value from one register to another. It's more that we're copying it into another register, but the old register retains its value. So in a sense, the load immediate and move instructions do the exact same thing. They write something to a register through the write data port. And what they write is either a value of another register or an immediate. But the underlying operation is the same. We're basically just storing an operand into the register file. And there's quite a few other instructions that work like this. For example, you might want to have a jump instruction that can jump to a fixed address coming from the instruction stream. But also you might want to have a flavor of it where the address you're jumping to is coming out of a register, so you can compute a destination address. Another good example is addition, where you might want to have an addition that just adds a fixed constant value to a register, and you want a complementary addition that just adds two registers together. Or you might want to have a shift where the shift amount is a constant and is given as part of the instruction, and complementary a shift where the shift amount is read from a register. So it's actually fairly common in processor design to have the second operand be either a register or an immediate, because a lot of instructions want to deal with both of them in one way or another. And so an easy way to achieve this is to add a tri-state buffer, basically a buffer with an output enable, identical to the ones we've used in the register file to select one of the registers to drive their value onto one of the read ports. And so the input of this we connect to the immediate bits coming from the instruction, and the output we connect to the read data bus of the register file. And so with this setup, when we select the register for reading and disable the tri-state buffer, we essentially get the register's value as the second operand. When we deselect the registers, RD2 is no longer driven, and once we enable the tri-state buffer, we actually get the immediate as operand number 2. In order to make sure that we can control whether the register file drives RD2 or not, let's add a read enable for the second read port. This is like an output enable for the RD2 port, which allows us to make the register file release RD2 and go into a high impedance state, such that it can drive a different value from the outside. We want this read enable to be the exact opposite of the enable that we feed into our tri-state buffer, which you can pretty easily accomplish by feeding the tri-state buffer enable into an inverter and using the result as an enable on our register file. This gives us a pretty handy control line, which we can call something like op2 is immediate, that we can use to pick what gets put on the op2 bus, either the register value or the immediate value coming from the instruction. Now, whenever the tri-state buffer is enabled and is driving an immediate value onto the op2 bus, the register file is disabled. And conversely, whenever the tri-state buffer is disabled, the register file is enabled and can drive a value onto op2. Now for these first instructions that we want to have, we can connect the op2 bus directly to the write data port of the register file. This will allow us to pick either an immediate or a register value and write it back to the register file. And in the future, we'll add a proper write-back bus that allows different parts of the CPU to write things back into the register file. For now, this direct wire is good enough. So when we set this operand 2 is immediate flag to 0, the immediate tri-state buffer is disabled and the register file report is enabled through the inverter. This makes it drive the selected register onto the op2 bus. And since we have connected op2 to the write data port, we can pick one of the registers to store this value into. So we read a value from one register and store it into another register, which is exactly the move instruction we were after. And when we set the operand to isImmediate flag to 1, the situation reverses. The immediate buffer is enabled, and the register file report is disabled through the inverter. This prevents the register file from driving and allows the tri-state buffer to drive the immediate value onto the op2 bus. And again, since op2 is connected to the write data port, we can pick a register to store this value into. So we take the immediate bits from the instruction and store them into a register, which is that load immediate instruction that we were looking for. So let's go build the circuitry. So in order to choose for the second operand to either come from the register file directly through RD2 or through an immediate value, we'll want to add another one of these buffer chips here, where we can basically say if we don't read any of the registers, which is basically saying nothing drives a value onto the RD2 bus, we can enable that buffer and use it to drive the upper bits of the instruction onto this bus. This will allow us to either pick one of the registers and have the register's value driven onto RD2, or the upper immediate bits of the instruction and have that appear on RD2. So let's do that. First up, let me add another breadboard down here so we have some more room to work with. And then as per usual, let me add a decoupling capacitor to the new power rail down here. And we'll want to connect the power rails immediately. And let me add another one of these 74HC541 buffers here in order to drive the immediate value onto the bus. And we'll line it up nicely with the one above. Let me hook up power and ground. And now we'll want to connect the outputs of this buffer up to the rest of the bus up here. Basically the same thing we had up here, where we have a few jumper wires just jumping back down. And we're going to do the same thing down here. Alright, so the outputs on the upper side of the chip here are now connected up to the RD2 bus. The bottom side of the chip is now basically our immediate value input. So we're going to take the upper 8 bits of the instruction and we're going to feed it down here. This buffer will allow us to then optionally drive it onto the RD2 bus. Now the 74HC541 chip has two output enable inputs, one at the bottom and one at the top here. They both basically have to be low for the output to be driven. And since we're only going to need one of them for now, we can just tie one of them low. Alright, that's one of the output enable pins. And then the other one, we might want to attach an LED like we did up here so we can actually tell who's driving onto the RD2 bus. The LED needs some power. So this is basically a copy of the two setups we have up here. So it's pretty straightforward. Now we have two options to drive a value onto the RD2 bus. Either a register is driving, which we've been doing by changing the read address to up here, which basically selects one of the registers, or it's this buffer down here. But now we're in the situation where we never want to have this buffer and one of the registers drive at the same time, because this will produce a drive conflict on this bus and create short circuits through the register file, which we want to avoid. And now one option would be to just say whenever we want to drive an immediate value onto RD2, we're just going to select 0 as the RA2 input. And that would be an option because the 0 input we have left disconnected. So if we select read address 0 here, what will basically happen is that none of the registers is selected. That will basically release this bus and allow us to have this buffer down here enabled. Now for us, it's going to be easier if we don't mess with the read address here and don't try to zero it out in order to deselect any of the registers. But these 74HC139 chips that we've used to actually turn the 2-bit register address into a 4-wire select signal, which we can route to each of the registers, these have an additional enable input, which we haven't used. We've just tied it low to enable it all the time. But we can use that input to actually disable the selection of any of the registers. these outputs are all active low. So basically what happens is all the wires are high except for the one that is actually selected based on the input. That one is being pulled low. And if we disable the decoder by pulling the enable input high, what will actually happen is that all of the outputs go high and basically disable all of the output buffers that we have here. Now the output enable of this chip is an active low input, and so is the enable input on the address decoder here. So what we need is an inverter here such that we can flip the output enable bit of this buffer here and apply the inverted version of that to the address decoder up here, which will basically allow us to either read the registers or drive the immediate value onto RD2. So let me add a 74HC04 chip, which is basically 6 inverters in a box. And I think we'll just place this right down here next to the buffer chip. Let me hook up power and ground. And so now we want to connect the output enable of this buffer down here to the output of one of these inverters. Let's just use the rightmost inverter. And now the input of the inverter we want to hook up to the enable input on the RA2 address decoder, which is currently tied low up here. And now we remove the ground connection up here. All right, and this input to the inverter here, which is directly connected to RA2, the inverted version is connected to this buffer. This is now basically our operand 2 is immediate signal. So when we pull this low, the registers are enabled and one of the registers will drive. And if we pull this high, the registers will be disabled. And the inverted output is going to enable this buffer over here, which is going to drive the immediate value onto RD2. So that's the register or immediate selection done over here on the RD2 side. But now we also want to drive something onto the write data bus. And so let me actually bring down the write data bus further onto this breadboard so we have an easier time connecting to it. All right, so that's basically our write data bus now down here. Now, as a first setup, all we ever want to write to a register is going to come from this RD2 bus because it's either another register's value, which is coming from above here, or it's going to be an immediate value, which is going to be driven onto RD2 by this buffer here. So for the time being, let me actually just connect the RD2 bus directly to the write data bus of the registers. At a later point, we want to be much more clever about what we actually connect to the write data bus because we have other sources of data that we might want to write into a register. For example, the result of an addition or something loaded from memory. But this will do for now. And now as a last step before we can test this out, we've used these wires up here to directly wire a value to the write data bus. But we do have this connection here now, so we no longer need these wires. And so instead we can use these wires to actually hook up an immediate value to this buffer that we've added to test it out. Okay, so let's actually test this and see if we can basically simulate what a load immediate instruction would do. And let's try to load a few values into the registers. And then let's try to see if we can emulate the move as well, where we try to copy stuff between the registers. So let me power this up. Okay, that looks good. So let's change the read addresses to 0, so we're not actually reading any register. All right, so all the lights are off. Now let me wire an obvious pattern into the immediate input. Let me just make the upper 2 bits a 1. There we go. And so now if we enable this operand 2 is immediate input here, we should actually see the immediate value that we have here being produced on the RD2 bus. And that is actually the case. So pulling this high is going to enable the buffer down here, which is going to drive the immediate value we have configured with the wires here. It's going to drive it onto RD2, and we can see it here. And since we've connected the read data 2 bus to the write data bus, we actually see the same value appear at the write data bus as well. So let's actually select register 0 for writing. That enables this register's clock. Let's toggle the clock. And as you can see, register 0 is now loaded in the immediate value we've presented here. Let me change the immediate value we have here, and instead of the upper 2 bits, let me enable the lower 2 bits. And so the value already shows up on the bus here. Now we're going to select register R1 for writing. And if we toggle the clock, the immediate value that we've configured is stored in register R1. That's pretty cool. Now this is the load immediate functionality working, but can we also copy a value from one register to another? Let's give that a shot. So first, we no longer want to actually have an immediate value as the second operand, but we want instead to read this from a register. So we disable the op2 as immediate line, which makes the immediate value disappear. And now we're going to select register 0 for reading on RD2. And as you can see, register 0's value shows up on RD2. And it also shows up on the write data port because we have this connection here. And now R1 is still selected as the register to be written. So if I toggle the clock, we should see the value in R0 being copied over into register R1. And that's exactly what happens. Let's try a different value. So we'll load another immediate, enable the operand 2 is immediate line. Let me change the bits a bit. And now we'll leave R1 selected as the register to be written. And so if I toggle the clock, we see this new immediate value being written into R1. And now we disable the operand 2 is immediate flag again. And let's select R0 for writing. And let's select R1 for reading, such that we can copy the R1 value into R0. So that's the R1 value being produced on the RD2 bus. And now if I clock the register file, the value gets copied into R0. Fantastic, this already works really well. Now you might say 2 registers, it's not really useful because as soon as you do a move operation, you're basically destroying the only other value you have in the register file, and it looks just like this. It's just 2 identical values. But this becomes much more useful if we have more registers. For example, if we say expand to 4 or 8 registers, it becomes very useful to move values between the registers and being able to load an immediate value into the register file. So we've extended the register file with the ability to support move and load immediate instructions, but there are no such instructions yet. So let's see how we can actually extend our instruction encoding such that we can have actual move and load instructions that we can include in our program and make use of. This is how the instruction encoding looks like at the moment. The lower 2 bits of the instruction control the program counter, which allows us to do jumps. And the upper 8 bits of the instruction contain the jump address or the jump offset. And the remaining 6 bits we have here, we haven't been using at all. The register file we've built together with the changes we just made introduces a few new signals that we need to connect. First up, we have 3 register addresses to drive, 1 write address and 2 read addresses. And we have this op2 is immediate flag that we can use to pick a register value or the immediate value in the instruction. At the moment, the register addresses are just 2 bits, but we'll want to expand those to 4 bits in the future, such that we can have up to 16 registers instead of just the 4 that we could have with the 2 bits. That's a total of 13 additional bits that we would need, but we only have 6 unused bits left in the instruction. So as it stands right now, we just don't have enough bits in our instructions to control all these new signals. To work around this limitation, let's look at how computers commonly address the registers within their instructions. With 3 address instructions, each instruction encodes its 2 input registers and its output registers separately. This is the common encoding in reduced instruction set computers or RISC machines, where instructions are often made larger and they contain more information in an attempt to make the instruction decoding in the processor a lot less complex. Here the add instruction, for example, encodes that its 2 source registers, RS1 and RS2, are added, and then the result is stored in the destination registers RD. In contrast to this, most early computers and complex instruction set computers or CISC machines in general have 2 address instructions, where each instruction only encodes 2 distinct registers. Here the add instruction encodes that its source register RS and destination register RD are added, and the result is stored in the destination register RD. The first register operand does double duty and acts as both as a source register and the overall destination register of the instruction. This two-address encoding is exactly what we are going to use, since it saves us an entire register operand in the instruction. And so as a result, we'll connect together the write address and the first read address port of the register file, such that the first operand in the instruction is both used as a source register that we read and the destination register that we write. So let's see how we can connect these signals up to our instruction bits. First up, we'll keep the lower bits as the program counter mode to control jumps. Then we'll use bits 4, 5, 6, and 7 as our first register operand. This will be our destination register, and since we are using two-address instructions, this is also our first source register. So instructions will be able to both read and write the register that we put into these bits. The upper 8 bits of the instruction we've just used for the program counter so far, but now that we have a more generalized notion of an immediate value encoded inside the instruction, these are no longer just jump addresses and offsets. Now, one neat thing about that new up to is immediate flag is that we either read a second register or we use an immediate value, but never both at the same time. This means that we can split these upper bits of the instruction up and use bits 8, 9, 10, and 11 as our second register operand. And then all of these 8 bits together also form the immediate value. And then to pick between the register mode, where we use bits 8 to 11 as a register operand, or the immediate mode, where we use all of the upper bits as the immediate value, we'll hook the up to is immediate flag up to bit 3 in the instruction. And so an instruction can basically encode with its bit number 3 how it wants the processor to interpret the upper 8 bits. Should it be an immediate value or should it be a register to be read? And finally, bit number 2 we'll leave just unused for now. So that's all signals accounted for. Time to wire things up. So I've brought the other half of the build back. Now the question is, how do we actually hook this up and get everything connected? And so what's basically happening here is we're taking the upper 8 bits of the instruction and we're bringing it over here, and then from here we're bringing it to the absolute address input of the PC for absolute jumps, and we're also bringing it into the relative offset input for the relative jumps. But now, instead of having this direct connection, what we actually want to do is we want to feed these upper 8 bits of the instruction, which is where we keep our immediate values. We want to feed this into this new immediate value input we have close to the register file. And then we want to take the data produced on the read port 2 of the register file and use that as the absolute and relative addresses. And this will give us the flexibility to feed these inputs of the program counter either from an immediate here or from a register value, which we haven't been able to do before. First, let me remove these wires here. And so instead, we're going to take this ribbon cable here and connect it directly to the immediate input over here. All right, so that's the immediate bits of the instruction hooked up to the immediate input here on the register file. Next up, there are these PC connections here, which we'll want to bring over and take from the RD2 bus. And then there's the relative jump offset over here. We might need a longer cable for this. Let's try this longer cable. All right, so that's the immediate value going in here. And we're now feeding the 2 inputs of the program counter directly from the read data to bus. Now, besides this, we also have the write address and the 2 read addresses that we need to connect to the instruction bits over here. And so as we've discussed before, we're going to use the same value for the read address 1 and the write address, such that the first register that is mentioned in the instruction is a register we read, and we can also write. So let me connect those up. Don't need the write address connection here anymore. And then we'll use this here. Make sure that I don't accidentally flip the bits. And so now the write address and the read address 1, we are going to take from bits 4 and 5 of the instruction. Let me use a long cable for that. And then we'll connect that up to bits 4 and 5 of the instruction. It should be right there. And in a similar fashion, we want to connect read address 2 to bits 8 and 9 of the instruction. Then on this side, this will go into 8 and 9 as we discussed, which is here. And over at the register file, we also have this operand 2 is immediate flag that we need to hook up. This we've said we're going to connect to bit number 3, so let's do that. And then we can remove this connection. And then other connections we need to make is we need to connect the power rails of the two breadboard stacks. And then on the register file side here, we have this clock input here that we've been toggling manually basically. And we actually do have a proper clock in the design, which we've been wiring pretty haphazardly like this. I think it's time we actually clean this up a bit and we bring the clock over to maybe a central point right here. And then from that point, we're going to distribute it to the program counter, to the instruction fetch and the program memory here, and also the register file right here. So I'm going to disconnect this. Then I'm going to bring over this clock wire to this more central point, let's say here. And then we'll take the clock that we feed into the program counter and we feed this to this connection here. And we'll use a shorter wire here to connect back up to the program counter, like so. And so all that's left is actually hooking up the clock here. From here, gonna go all the way over into the clock here. Can remove this wire and that should be it. So to recap what we just did, we took the immediate bits from the instruction and we wired it over into the immediate input on the register file side. Then we rewired the relative offset and the absolute address inputs of the program counter to, instead of coming directly from the instruction, it's now coming from the read data bus number 2 on the register file, which is also the place where we can select between register value or immediate value. We redistributed the clock a bit. We're feeding the write address and the read addresses from fields in the actual instruction right now. So these are actual instruction bits that select which register we are operating on. And furthermore, we've used this operand 2 is immediate flag here, and we connected it directly to the instruction. So we have a bit in the instruction now that will actually allow us to choose whether we want to read a register value or whether we want to use the upper bits of the instruction and just drive those as our second operand. And so since we've changed the wiring a bit and the instruction encoding is different, nothing's going to work out of the box. So let's actually write some software for this and see if we can make this work. All right, so let's update our instruction set architecture with the new bits that we're now using in the instructions. So at the top, this was basically the old encoding that we had. This we can just delete. So first of all, let me make things a bit more readable and replace these X's with dots, so it's more obvious where the interesting bits are. All right, so the bits that control the program counter, they stay the same, so we'll leave this as it is. And then let's add the new connections we have. So this is the operand 2 is immediate bit that we have. If it's 0, we are selecting the output from the register file, and if it's 1, we're driving the immediate bits from the instruction onto the operand 2 bus. Next up, we have connected the register addresses to the instruction bits. Bits 4 to 7 are the first register operand, which we call RD for destination register because it's the one we can read and write at the same time. And then bits 8 to 11 are the second register operand, which we're going to call RS for source register because it's the register we can only read but not write. And then the upper 8 bits of the instruction no longer go into the program counter directly, but they're more general, the immediate bits right now that we use to encode just a constant value as part of the instruction. All right, so that's our encoding. These are the bits that we can set in the instruction. Now we might actually want to update the instructions themselves, so we have a full list of operations that the processor supports, and we also know what concrete binary and hexadecimal patterns correspond to those instructions. So the NOP instruction stays the same. It's just going to advance the program counter and won't do anything with the other operands. As the first new instruction, let's add the load immediate, which will basically take the upright bits, the immediate bits of the instruction, and store it in a register of our choice. So let's see how we can encode that. So we're going to need the immediate bits in the instruction. And then we have this RD operand, the destination register, which basically indicates where we want to store this immediate. And we also want to indicate that the second operand, the one that we're trying to write to a register, is an immediate. And then bit number 2 is unused, so we just put in a 0. And as far as the program counter is concerned, we just want to be in stepping mode. Now in hexadecimal, this is going to be II, and then the next 4 bits are going to be the destination register address, and the lower bits are going to be an 8, the 1000. So that's our first new instruction. And now alternatively, instead of writing an immediate to a register, we'll also want to move a value from one register to another. This time we're using both the destination and the source register operands. The upper 4 bits are not used, so we'll just set them to 0. And then we have the 4 bits corresponding to the source register's address. And then the next 4 bits correspond to the destination register address. And now the second operand is a register this time, not an immediate. So this bit is a 0. Then bit number 2 is unused, so we'll just set it to a 0. And we'll just want to be in stepping mode. All right, and converting this to hexadecimal, this is going to be a 0 for the top 4 bits. The next 4 bits are going to be the source register, then the destination register, and the lower bits are 0. Great, so that's our new instructions that load values into registers either from the immediate bits in the instruction or from a different register. Now the program counter no longer takes the absolute address and relative offset directly from the upper bits in the instruction, but we've changed it such that it now takes those from the second report of the register file. So what we can do is we can introduce new flavors of these jump instructions. So no longer do we just have a jump relative with an immediate offset. We actually have 2 flavors. We have a jump relative with immediate and a jump relative with register, which uses the value in a register as the jump offset. So let's update these instructions here. So these are going to be our 2 new instructions, jump relative with immediate, jump relative with register. Now let's think about the encoding for these. The only thing that changes for the immediate flavors is that now we actually have to indicate in the instruction that the second operand, the one that we're using as an input to the program counter, is supposed to be an immediate. So for the immediate flavors, we'll have to set bit 3 to a 1. And now this changes our hexadecimal encoding of the instruction. This here is a 9, 1001, and here is a 10 in hexadecimal and A, the 1010. And then let us look at the register flavor. Again, instead of having the topmost 8 bits of the instruction be the immediate, we're now using a source register. So the topmost bits are unused, and then the next 4 bits are going to be the source register, and the rest will just keep the same. We're not using any destination register, so the next 4 bits are going to be 0. And then the operand 2 is immediate flag has to be 0 because we want the register value to be our second operand. And then this changes the encoding a bit. Topmost 4 bits are 0. The next 4 bits are the source register, and the rest we have not changed. Now let's do the same for the absolute jump with register. Again, same thing, topmost 4 bits are unused. Then we're dealing with the source register. We're not using any destination register, and the operand 2's immediate flag is set to 0, such that we're actually loading the register value. This also changes our hexadecimal encoding, and the rest remains the same. So these are all the instructions our CPU now supports. The knob we already had before, but now we have these 2 instructions that deal with registers and the data movement into and between them. And we have new flavors of the jump instruction, which now can actually jump based on what's in a register, which is kind of cool. Now we'll also have to update the pseudo instructions. If you recall, these were basically just absolute jumps with a predefined immediate value at the top. But now, since we now have this op2 is immediate flag, we have to indicate in bit number 3 that we actually want these top bits to be interpreted as an immediate. This again changes the encoding. And so down here we have this sample program that we have loaded into the program memory the last time and that we've executed. Let's actually get rid of this and write a completely new program that makes use of these instructions that we have created. Now, when we reset the processor, the registers actually can come up in basically an arbitrary state because we're not resetting the registers themselves. So they have a random value contained in them. So as a first step, we could try to clear the registers. So as a first instruction, let's actually load the value 0 into register R0. And then let's use the move instruction to move this value also into register 1. Now let's try to do an absolute jump with immediate, and let's just jump to an address slightly ahead in the program. For example, address hex 10. And then we'll continue at address hex 10 with our program. And now let's load some more interesting values into the registers that are easy to visualize. First up, let's load F0 into register 0. This is basically the upper 4 bits set and the lower 4 bits cleared. And let's load the hex value 55 into register 1. This is an alternating pattern of 1s and 0s. Then after this, let's try a relative jump, but this time with the register. So instead of providing the jump offset directly as part of the jump instruction, let's load it into a register first and then jump based on that register. So basically what this will do is it loads the value 6 into R0 and then jumps using that as an offset. And basically we're just going to skip the next 2 instructions and jump to the address 6 bytes ahead. And so let's actually fill in the gap with NOP instructions. So this is where we will jump to. Let's do another absolute jump, but this time, because we've already done an absolute jump with an immediate, this time let's do an absolute jump with register, and let's load the target address into a register. And as we did above, let's just jump ahead to a different address in the program memory, maybe hex 40, and then we continue the program there. So we load the value hex 40 into register 0 and then do an absolute jump based on register R0. So our program continues here at hex 40. And now let's actually make some good use of the load immediate instruction that we have. And let's create an interesting LED pattern in the register file. For example, a walking bit pattern. So first up, we load hex value 1 into R0. This will light up the first bit. Then the hex value 2. This is going to be the next bit, and so on. And then let's do the exact same in reverse, such that the bit walks back. And so last but not least, we have tried our 2 absolute jump flavors, but we only tried the relative jump with register. So let's do a relative jump with immediate. And let's maybe jump back up to the start of this pattern on the LEDs, such that basically when our program runs, it will enter this loop at the end of the program and basically forever display this, this pattern on the register file LEDs. And so we want to jump back to address hex 40, but we need a relative jump offset here. And if we look at the instructions that we have here, these are actually 16 instructions. And so 16 instructions with 2 bytes each is going to be a 32 byte jump offset backwards. Alright, so this is our new program. All that's left to do is to actually assemble it. We've just typed down the human readable form of the instructions, but our processor needs the actual bit patterns, or at least the hexadecimal representation, so we have something to store into the program memory. So let me split this window up so we can actually see the encoding while we're doing the assembly by hand. So on the left-hand side, we have our instruction encoding, and on the right-hand side is our program that we need to assemble now. First, the LDI. The encoding for the LDI is the first 2 characters is the immediate, that's a 0. The next character is the destination register, that's register 0, which if you recall is address 1, because we left address 0 as kind of indicating that we don't want any register access. And finally an 8. The move has a 0, then the source register, which is register 0, so it's address number 1. Then the destination register, we're writing into register R1, so this is going to be address number 2. And finally a 0. Next up, the jump instruction. The absolute jump with immediate, the first 2 characters are the immediate, so that's a 10. Then we have a 0 and an A. Alright, next chunk of the program. Again, load immediate has the immediate in the upper bits, F0, then the destination register, that's address 1 for register 0, and then 8. Same story again, 55 for the immediate, address 2 for register 1, and then 8. Again, offset 6, register 1, 8. Now the relative jump, first character is a 0, and then it's the source register, and we want to jump to whatever is in register 0, so that's a 1, and the rest is just 0, 1. Knobs are trivial, all zeros. Then we do another load immediate, that's the 40 for the immediate, 1 for R0, and then 8. And then the absolute jump with register as a 0, then the source register, which is a 1, and then 0, 2. And the last chunk. Load immediate starts with the actual immediate value, and then a 1 for register 0, and an 8 to indicate the load immediate. Alright, and finally a relative jump with an immediate offset. Now this is minus 32, which in 2's complement hexadecimal is the number E0, and the relative jump with immediate is a 0, 9. Alright, so that's our new program. So let's take a look at what's currently in the program memory. Okay, and let's convert this from binary to hexadecimal so we can actually read and edit it. So that's what's in the program memory. You can see these look suspiciously like our last program. All right, let me split this up. And now we want to actually type these hexadecimal values here into the memory over here. And we're going to use some text editor magic to do that. All right, and now writing these to the memory is going to be easy. All right, and now all that's left to do is actually copy this down. We have the first few instructions, and then we jump ahead to address hex 10 because we have a jump at the end of the program here. And then we jump ahead again to address hex 40. And then finally this last instruction here. So that's our program ROM updated, at least in hexadecimal. So let's convert this back to binary and then write this back to the program memory itself. All right, let's go and try this out. It looks like coincidentally the processor came up in pretty much a fully reset state. But we're still in reset, so let me actually step it out of reset. All right, so we are at address 0, and our first instruction was a load immediate of the value 0 into register R0. So as you can see, the upper 8 bits of the instruction are cleared. There's the value 0, the immediate. Since we are dealing with an immediate, the up to is immediate flag is high, which means this 0 here is driven onto the RD2 bus. And we have register R0 selected for writing because this is our destination register. Nothing changes because the register was already at 0. Next up is a move of the value of register R0, which we are reading on the second port here. And we are moving this value into R1, which we are selecting for writing. And since we have this temporary connection here, whatever we read out of RD2 is going to be what we'll be writing back into a register. Again, no change because R1 was already at 0. The next up is a jump absolute with immediate. And in this case, the immediate is hex 10, which we can see up here. It's a 10. And this value is pushed onto the RD2 bus. You can see it show up here, 10, because again, the up to is immediate flag is set. And through this connection here, it's also making its way onto the write data bus. And the program counter is configured to do an absolute jump, as you can see here. And it's using the value on RD2 for its absolute jump. So what we expect to see is this value here, the one on RD2, the 10. We expect this to be copied into the program counter here. And as you can see, the 10 is now the current program counter address. Next up, we have a load immediate of the value F0 into R0. And as you can see, the F0, all upper bits set, all lower bits cleared, is produced onto the RD2 bus through the up to is immediate flag. And we are selecting R0 for writing. And as you can see, after I hit the clock, the value F0 ends up in register R0. Next up, we have another load immediate. The value is hex 55, and we are loading that into register R1. So the 55 is this alternating pattern of bits, and this gets put on the RD2 bus again as before, and the write data bus, and we're selecting R1 as our target register. And after clocking, the value ends up in R1. Next up, we're preparing a relative jump with a register. So we're loading the value 6 into register R0. And so the upper immediate here is the value 6. And as you can see, this shows up on the RD2 bus, and we're loading it into R0. And it ends up in R0. And now we're at the actual jump relative with register. And so this time we're not using an immediate, so the up to is immediate flag is not set, and we have disabled the immediate buffer down here. And what we're actually doing is we're selecting register R0 for reading on read port 2, and the program counter is configured to do a relative jump, which is going to take this value off of RD2, and it's going to use it as a relative jump offset. So what we expect to happen is we expect this program count here to increment by the value in R0, so basically by the value 6. And there you go. We skipped the 2 NOP instructions that were in this space, and we're now 6 bytes further ahead in the program. Now we're preparing another jump. This time we're preparing an absolute jump using a register again. And so what we're doing is we're loading the hex address 40, which is where we want to jump to. We're loading that into register R0. And so again, the upper immediate bits in the instruction, the hex 40 gets put onto the RD2 and the write data bus, and we're selecting R0 to write. And there you go, the hex 40 makes an appearance in register R0. And so next up is the actual jump absolute with register instruction. And so what we're doing is we're selecting R0 again for reading on the second read port. And the program counter is configured to do an absolute jump. So this is going to copy the value from RD2 into the program counter. So we expect the program counter to assume this value here, the value hex 40. And it does. And now at address 40, we have a sequence of 16 load immediate instructions. And what we're basically doing is we're loading a walking bit pattern into register R0. So again, register R0 is selected for writing. And we're basically just going to continuously copy the upper 8 bits of the instruction into R0. Pretty neat. That seems to be working. And now finally, after this pattern has completed, we have a final jump instruction. This time it's a jump relative with immediate, and we're doing a backwards jump by 32. So we have the value minus 32 here. It's an E0 in hexadecimal in 2's complement. This gets put onto RD2. And then as we've seen before, the program counter is configured to do a relative jump. This time the relative jump offset is actually the immediate that is produced on the RD2 bus. And so what we expect to happen is the address of the program counter here should decrement by 32. In this case, this basically means we should jump back to hex address 40, which is the beginning of this LED pattern. And as you can see, we're back at address 40, and the next instruction again is a load immediate into R0. This is the first step in our pattern. So let's just let this run and see how this looks. Pretty cool. So here you can see this walking bit pattern we have in register R0. And the program counter is basically performing this loop at the end of the program, which just runs through this pattern until we turn off the machine. So let's recap quickly what we just did. Basically, we started out with having this program counter and program memory as a separate build. And last time we have created this register file here where we have 2 read ports and 1 write port and nothing connected to that. And so what we did now is basically we have attached this additional breadboard down here. And what we did was add an additional buffer here that allows us to drive an immediate value onto the RD2 bus, such that we get a flag which basically says operand 2 that we read on the second port here is supposed to be an immediate, not the value read from a register. And then we cross-connected the second read port and the write port of the register file, such that whatever we read on this RD2 bus, which can be a value from a register, or through this up to is immediate mechanism down here, can also be the immediate bits of an instruction. Whatever that is, we have the possibility to write that back to a register. And then we went ahead and connected the read and write addresses of the register file up to bits on the instruction. And we also have this up to is immediate flag here that we hooked up to one of the instruction bits. And then we changed the program counters connection. We detached it from reading its jump target and jump offset directly from the instruction. And we changed it such that it actually reads it from this RD2 bus from the second read port on the register file. And this allowed us to expand upon our instruction set architecture, because now we have the possibility on the one hand to create load and move instructions which store values in the registers either from the immediate, in which case it's the load immediate instruction, or from a different register, in which case it's a move instruction. And on top of that, we were able to double up on our jump instructions. And instead of just having immediate jumps, we can now also use values coming out of registers to change the program counter, either to jump to an absolute target address or to do a jump relative to the current program address. And this has some really nice implications in the future, because there are uses for actually jumping to an address that has been computed in a register rather than an address that is kind of hard-coded in the program. These can be callback functions, or if we write an operating system, this might be the operating system jumping to a program that the user has loaded from some storage device, in which case you might not know upfront where that program is going to be loaded. So it's useful if we are able to actually jump to a destination that we compute on the fly. And this makes for a pretty big power jump in what the computer can do. One thing that was kind of cumbersome was that when we wrote our program, we first wrote it in this human readable form, because it's very natural to talk about load immediate instructions, jumps and moves and different positions in the program. But in order to make our computer here understand what it is supposed to do, we need to convert that human readable form, we need to assemble it into its binary form. And for this program, we did this manually. We had an instruction set architecture, which was basically the list of instructions and how they're encoded. And we had our textual representation of what we wanted the program to be. And we basically manually just filled in the hexadecimal values of every instruction in the program. But this is really error prone and can get pretty cumbersome, especially as we want to write larger programs. So one thing we might want to tackle soon is actually writing a simple assembler program that can take the program in this human readable form and spit out this binary representation. And all it does is basically just fill in the gaps and fill in these hexadecimal values, the thing that we did manually this time. And now that we have some actual registers, it's just 2 at the moment, but that's already kind of interesting. The next step, instead of just jumping around based on the registers, is going to be to actually do some calculations with them. We might want to add 2 registers together, or compute a logical AND or operation, or shift things around. So it's going to be interesting to see what kind of arithmetic operations and logic operations we can come up with that we can do on the register file. So this worked out like a charm. I'm really happy with how this is coming along, and that we have registers now, and this is starting to look just a little bit like a computer. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.